China has quickly emerged as a new leader in robotic exploration of the moon. With each successive mission, the Chinese have made unprecedented gains in their ability to reach the surface of the moon with advanced scientific instruments and sample return capabilities. In their most recent lunar excursion, China has made their mark on some of the most valuable real estate that the moon has to offer, and that is just one small step towards a much bigger Chinese presence on the moon that will happen in this decade. On the morning of May the 3rd, a Chinese Long March 5 rocket launched the Chang'e 6 mission, the world's first spacecraft designed to retrieve samples from the moon's far side. About 37 minutes after liftoff, the 8,200-kilogram Chang'e 6 spacecraft stack separated from the rocket, entering its planned orbit of 200 by 380,000 kilometers. This started a complex 53-day mission, orchestrating 4 spacecraft, an orbiter, a lander, an ascender, and a re-entry capsule. On May 8th, China's Chang'e 6 spacecraft stack successfully entered an elliptical orbit around our moon, using a 3,000-Newton engine on the orbiter module to perform the braking burn, slowing the spacecraft enough to be captured by the lunar gravity. Shortly after, Chang'e 6 deployed Pakistan's 7-kilogram CubeSat called iCubeQ in orbit, making it the country's first mission exploring our cosmic companion. Developed by Pakistan's Institute of Space Technology with aid from China's Shanghai Jiao Tong University, iCubeQ hosts 2 optical cameras and a magnetometer. Scientists hope the orbiter will detect potential signs of water ice on the moon's poles. Now, following a 14-minute descent from an altitude of about 15 kilometers in its lunar orbit, China's Chang'e 6 lander successfully touched down on the moon's far side on June 1st, resting at 153.99 degrees west, 41.64 degrees south, near the southern rim of the 500-kilometer-wide Apollo impact crater. This marked China's 4th successful landing in 4 attempts. It's also only the 2nd ever far-side lunar touchdown after Chang'e 4. Much like most modern lunar landers, Chang'e 6 used several key technologies to descend onto a safe spot: a variable thrust engine, optical imagery, onboard maps, hover phases to detect hazards, and shock-absorbing crush core legs for the final freefall. Chang'e 6 also used a laser-based LiDAR sensor to map the local landing area in 3D before the final landing phase. This is a sped-up interpolated video from CNSA showing the view from Chang'e 6 during its lunar descent and landing. Interestingly, CNSA's new release also mentions landing aid from another sensor. To prevent interference to optical sensors by lunar dust during landing, the lander is also equipped with gamma-ray sensors to accurately measure the height through particle rays, ensuring that the engine can be shut down on time and the lander can touch down smoothly on the lunar surface. So in the span of 1 week, Chang'e 6 successfully touched down on the moon's far side, collected up to 2 kilograms of soil and rock samples using a still drill and a movable complementary surface scoop, as well as context-providing lander instruments including cameras, a ground-penetrating radar, and a mineral spectrometer. The lander then used its arm to move the samples to a sealed container, deployed a small 5-kilogram rover to tactically photograph the lander, and launched the samples to lunar orbit as part of an ascent module on June 3rd, which autonomously determined its position and orientation with aid from the Chuichuao-2 communications relay lunar orbiter, and then docked with the Chang'e 6 orbiter on June 6th, following 4 orbital adjustments, about 30 minutes after which the lunar samples were transferred to the Earth return capsule. On June 21st, the Chang'e 6 orbiter module hosting the sample capsule began its journey towards Earth. When 5,000 kilometers away from Earth on June 25th, the orbiter module released the roughly 300-kilogram re-entry capsule, which later performed a bounced atmospheric re-entry, then safely descended and landed in China's northern Inner Mongolia Autonomous Region. That was one impressive way to perform a very nominal mission, including the orchestration of many modules, the kind that will help China land humans on the moon, which the country hopes to achieve by the end of the decade. China is so far the only nation to have performed robotic rendezvous and docking at the moon. These Chang'e 6 lunar samples are scientifically even more valuable than the previously collected Chang'e 5 samples. Since the Apollo crater is embedded in the moon's largest, deepest, and oldest crater, the 2,500-kilometer-wide South Pole Aitken Basin, the diversity of materials within the Chang'e 6 samples could help scientists worldwide solve a whole host of moon mysteries, such as understanding the distinct lunar farside volcanism and why the far side is so enigmatically different from the familiar near side, which is necessary to understand not just the moon's evolution, but that of our solar system as well. Since Chang'e 6's surface mission was on the moon's far side, the side we can't see from Earth, mission operators commanded the lander and received data from it via the recently launched Chang'e-2 relay orbiter. This orbiter will also relay communications for China's upcoming Chang'e 7 and Chang'e 8 landers. More on both of those missions in a minute, which are currently targeting launches in 2026 and 2028 respectively. The Chang'e-2 mission is testing and verifying technologies that will feed into the upcoming Chang'e satellite constellation, the world's first lunar navigation and communications service. The Chang'e constellation could also provide communication support for China's first crewed moon landing, currently targeting a launch by 2030. The Chang'e 6 lander carried 3 instruments from Europe: the negative ions at the lunar surface payload from ESA and the Swedish Institute for Space Physics, the French Space Agency's detection of outgassing radon detector, and Italy-based SCF Labs' INRRI retroflector. ESA's NILS already detected negatively charged particles on the moon's far side, a world first. These particles are produced due to highly energetic solar wind particles slamming the moon's surface and kicking up secondary particles. NILS is the first European instrument to operate from the moon's surface and is also Europe's first such collaboration with China. Beyond that, ESA has been providing ground station tracking and orbital confirmation support for Chang'e 6, similar to how ESA has been helping ISRO's Chandrayaan missions. The DORN instrument was intended to measure the noble gas radon leaking out of the moon's surface, which could provide independent evidence that our moon and Earth do indeed have a common origin. DORN also studied volatile gases, such as water vapor in the moon's exosphere. The INRI retroflector will reflect laser pulses from lunar orbiters in the future to get precise distance measurements and aid their navigation. CNSA is targeting the launch of their Chang'e 7 lander and orbiter in 2026. The lander, after touching down in one of the key identified landing regions on the moon's south pole, will deploy a rover and 1 or 2 hoppers. Similar to the NASA Viper and JAXA ISRO LUPEX missions, one of the Chang'e 7 elements will use a drill to sample materials in nearby permanently shadowed areas from varying depths. These will be fed into a heating furnace for the onboard lunar water molecule analyzer to detect water ice and other volatile resources like ammonia. Chang'e 7 will also carry a ground-penetrating radar to map the local subsurface, make local magnetic field measurements, and carry spectrometers to measure the composition of the local lunar material. In a similar vein to the seismometers selected to fly to the moon on the NASA-funded Draper-led CLIPS mission and Artemis 3, Chang'e 7 will have one to help scientists better understand the lunar interior and also constrain the rate of seismic activity and the amount of micrometeorite impacts on the lunar south pole, which will help safely plan lengthier crewed missions to the region in the future. Also, on April 24th, CNSA announced that Chang'e 7 will carry 6 international scientific instruments. The orbiter will carry a hyperspectral mineral mapping camera made by Egypt and Bahrain, a 3-kilogram instrument duo from Thailand to study solar storms and cosmic rays, and a Swiss-aided radiation monitor to measure incoming and outgoing radiation to and from Earth. For Egypt, Bahrain, and Thailand, this mission represents their first study of the moon. On the other hand, the lander will carry a Russian lunar dust and plasma analyzer, a telescope from the International Lunar Observatory Association, and another reflector from Italy-based SCF Lab, just like Chang'e 6. The Chang'e 7 lander was supposed to carry UAE's second lunar rover too, but the partnership was apparently blocked by the US export control rules. Now, some might say that the Chang'e 7 candidate landing site near Shackleton Crater is the same as what NASA desires for the Artemis 3 crewed moon landing mission. Gizmodo titled this article "China Oversteps NASA in Choosing Coveted Shackleton Crater for its Moonlander." So did China really choose the same lunar landing sites as the US? Well, that's questionable. Firstly, it was always likely and known that the robotic Chang'e 7 would land on the moon's south pole before the crewed Artemis 3 mission did. So can we even call the former to be choosing the same site as the latter? Artemis 3 has 13 candidate landing zones at the moment, which is not exactly a selection. More importantly, Shackleton is a big 21-kilometer wide crater, and the number of mission-favorable areas on the rim and nearby ridges are relatively plentiful. Even if both missions ultimately chose Shackleton as the main landing region, they may be reasonably far away, not just in time, but in space too. While yes, the water-hosting lunar South Pole not being a massive place could eventually mean potential contest between countries and companies for some common sites, but much before that comes the fact that there are purely engineering and scientific factors that make landing site selections converge to some locations. For example, the sun perpetually circling the lunar polar horizon, coupled with rocky terrain, automatically render high-altitude areas desirable power-wise for touchdown, which is what most lunar polar missions end up converging to. Scientists and engineers on both sides of the ocean understand these technical factors, but they aren't the only ones in the space chain. Such factors should be considered first before jumping the gun with policy recommendations and changes that are based on shallow narratives. Again, these could also adversely affect international cooperation and collaboration. Ultimately, alarmist propaganda also makes discussing the real challenges more difficult. Now, after CNSA's upcoming Chang'e 7 mission helps scientists get a tactile sense of the true nature and accessibility of water ice deposits on the moon's south pole, the agency will follow it up with Chang'e 8 2 years later. Launching on a Long March 5 rocket in 2028, the mission will comprise a lander, a rover, and an operation robot to collectively explore with 14 instruments the local geology and environment. Most crucially, with Chang'e 8, CNSA aims to test technologies most relevant to begin sending crew to the moon at the end of the decade. As Lingshin reported, CNSA called for domestic proposals for 9 out of 14 of the Chang'e 8 instruments in February. One such payload on the lander will melt lunar soil and transform it via 3D printing into parts that can be assembled. Another instrument will monitor and inspect this process. Chang'e 8's approximately 100-kilogram operation robot, which will move around quickly by lunar rover standards, will carry the 3D printed parts from the lander to a working area and assemble basic structures as a demonstration of in-situ utilization of lunar resources. The robot will also fetch rock and soil samples for the lander spectrometers to determine their chemical composition, which will likely include water ice. CNSA might leave some samples on the moon for future missions to retrieve them and bring them to Earth. Just like Chang'e 7, Chang'e 8 will have a seismometer to help scientists better understand the lunar interior and also constrain the rate of seismic activity and amount of micrometeorite impacts on the lunar south pole, which will help safely plan long-duration crewed missions to the region in the future. What's also notable about Chang'e 8 is that China has further increased the scope of international contributions. While Chang'e 6 and 7 each offer space for 15 to 20 kilograms of international instruments, China has been accepting proposals for scientific instruments, technology payloads, and even system-level contributions equaling up to 200 kilograms for Chang'e 8. As Andrew Jones reported, CNSA is expected to announce selections for the same by Q3 this year. China has made systematic progress with their moon missions. The successful lunar orbiters Chang'e 1 and Chang'e 2 led to the moon landing of Chang'e 3 in 2013, which in turn led to the farside lunar landing of Chang'e 4 later in the decade. CNSA once again upped engineering complexity by bringing lunar samples to Earth with Chang'e 5 in 2020, and then did it again with Chang'e 6 collecting the first ever samples from the moon's enigmatically distinct far side. And with Chang'e 7 aiming to provide scientists with a tactile sense of the true nature and accessibility of water ice deposits on the moon's south pole, followed by Chang'e 8, demonstrating technologies like building 3D printed bricks out of lunar soil, the two missions will allow China to continue charting a clear path that leads to putting humans on the moon by the end of the decade, work on which also seems to be progressing well. At a recent press conference, leading officials from the China Manned Space Engineering Office said that elements of China's first crewed lunar landing mission have progressed into prototype production and test stages. While not yet announced, it can be expected that China will conduct at least one uncrewed lunar landing and a crewed lunar orbital flight before attempting to land humans on the surface. China's crewed moon landing plan involves building a giant new rocket called Long March 10, which will take off from a new launch pad in Wenchang. The Long March 10 will be capable of sending 27,000 kilograms of payload on a trajectory to the moon, matching the performance of NASA's current SLS rocket and more than tripling China's ability to send payload to the moon compared to their current best Long March 5 rocket, from which the 10 is derived. Andrew Jones reported in May 2023 that China began using a new advanced facility in Tongchuan dedicated to test-firing huge rocket engines, including the ones being prototyped and built for the Long March 10. China recently tested firing 3 YF-100K prototype engines in preparation towards making the first stage of Long March 10. For the crewed landing mission at the end of the decade, a Long March 10 rocket will launch a 26,000 kilogram spacecraft named Mengzhao Y, which will carry 3 to 4 astronauts to lunar orbit. There, it would dock with the similarly massive Lanyu lunar lander, itself launched on another Long March 10. After the docking, 2 astronauts will transfer to the lander for a lunar touchdown and return to orbit after exploring the moon for at least 6 hours and possibly a few days. In July 2023, the China Manned Space Agency solicited science payload proposals for the mission's lander. Similar to the instruments NASA will deploy on Artemis 3, CMSA wants these payloads to focus on lunar geology, physics, life sciences, and solar and astronomical observations. On June 11th, the China Manned Space Engineering Office added 10 unidentified astronauts to its taikonaut core, some of whom might fly on China's crewed lunar missions starting at the end of the decade. Similar to ESA's Pangea campaign to train future lunar astronauts in geology and sample collection, which is a highly valuable skill during excursions on the moon, China will provide geology field training to astronaut candidates, followed by activities in mission-specific training simulators akin to Apollo. Through a CASC news release on April 26th, chief designer of China's lunar exploration program Wu Weiren revealed that the upcoming long-term moon base, called the International Lunar Research Station, will have an orbital presence too. While this element of the otherwise surface-based ILRS located on the moon's south pole will only exist circa 2045, the news page says the space station will be of considerable scale and host multiple continuous experiments. CNSA's Chuiqiao satellite constellation should be fully online by then to serve the navigation and communication needs of the many orbital and surface lunar assets operated by China and its currently about 24 partners. China aims to have 50 nation partners and 500 international organizational collaborators for ILRS. Following China's first crewed moon landing, currently targeting 2030, the country will focus on building the surface phase of ILRS by 2035. Key to realizing this is a new super heavy lift and eventually reusable rocket called the Long March 9. China announced in April that it aims to test a Long March 9 by 2032. The rocket can put 50,000 kilograms of spacecraft hardware on a moonward trajectory, which is almost twice the performance of the Long March 10 and NASA's current SLS rocket, both of which will be used to send humans to the moon. Once the Long March 9 is operational, China intends to use it to deliver huge amounts of cargo and possibly even more crew to the ILRS moon base. The rocket will deliver critical infrastructure for sustainable surface hubs via missions named ILRS 1 through 5. This includes infrastructure for energy needs, communications, transportation services, including landers, rovers, hoppers, and ascent vehicles, scientific research equipment, in-situ resource utilization technologies, and more. The ILRS moonbase will host large-scale science and technology experiments continually via remotely operated robots and, when available, humans. It was in 2023 that China finalized key scientific goals of ILRS, these goals being learning about our moon's evolution and structure, conducting lunar-based astronomy for doing cosmology and studying habitable exoplanets, observing the Sun and Earth from the scientifically unique vantage point of our moon, conducting lunar-based experiments like studying plant growth. Relatedly, Lingxin reported that by synthesizing data from CNSA's Chang'e 1-4 missions, NASA's LRO and Twin Grail orbiters, and ISRO's Chandrayaan-1 orbiter, China made the highest resolution geological map of our moon yet. The map, which took more than 100 researchers over a decade to compile, is free to use for non-commercial purposes, including lunar geology research and science communications. China itself is using the maps to support its growing lunar ambitions. The team is also working on furthering the map's resolution, including making high-accuracy derived regional maps suitable for advanced mission planning. Building on Chang'e 8 and China's first crewed landing, ILRS will also see multiple demonstrations related to extracting and using local lunar resources, such as water ice and melting soil, to create 3D printed structures. Relatedly, a recent document China submitted to the UN COPUOS concerning the legality of utilizing lunar resources suggests that the country sees such activities as permissible under current international law in much the same way the US-led Artemis Accords does. Some Western experts saw China's action as a positive development since it can now enable, in principle, a mutual dialogue for cooperative resource governance amid a decidedly international fora. In this explainer series, Professor Yun Zhao provides high-level context on China's legal space landscape and the lens through which the country might view such activities. If you enjoyed today's comprehensive moon update, be sure to subscribe to the Moon Monday newsletter by Jatin Mehta, linked down below in the description.